Hi everyone, my name is Yihan Lin. I'm gonna do the question 2 of homework 11. So let's begin. Okay, so it gives us some following functions of V, and they may represent an autocorrelation function of WSS stochastic process or a spectral density function. So it has to find out which functions may represent either or both and explain our answers. So we know that from the existence theorem, theorem first tells that for any non-negative function S omega, there exists a WSS process xt with S omega as its power spectrum. So for that, we know that if we can prove that the function S omega, which here we can set in V equals to omega here, and we can have an S omega here, and if we prove that it is a non-negative function, then we know it can represent a spectral density function. And from the existence theorem 2, we also have for any non-negative definite function RT1, T2, there exists a process xt with RT1, T2 as its autocorrelation function. But here it can be really hard to prove that this RT1, T2 is a non-negative definite function here. So here we may use some sufficient and required condition here. We know that if it is can represent as an autocorrelation function, we must have that R minus tau and R tau be even. And we know that R tau is actually smaller or equal to R0, and we must have this Fourier transform is non-negative here. So then we can prove first for subfunction A, it is fv equals to the minus absolute value of v's power of e, and here we set this v equals to tau, and we have our tau equals to minus absolute value of tau's power of e, and we know that it is even because it has an absolute value, and we know that r tau equals to this minus tau's absolute value of power of e is smaller or equal to r0, which is the 0's power of e, which equals to 1. And we know from the table its Fourier transform is 2 alpha over omega square plus alpha square, and here alpha is 1 and equals to 2 over omega square plus 1, which is non-negative. So we know then we know that this fv can represent autocorrelation function of a WSS stochastic process by setting v equals to tau. And by setting v equals to omega, we have as omega equals to the minus absolute values power of omega's power of e is larger than 0, which is then definitely non-negative. And we know it also can represent spectral density function. And for the subfunction B, it says fv equals to sine v squared over v squared, and we substitute v, we set v equal to tau, and we have r tau equals to sine tau squared over tau squared, and we know it is even because both square is even, and we know that r tau will be smaller than r0. Here we can only derive from limit tau to 0, sine tau square over tau square will be 1. And we know from the table also its Fourier transform will be like a function, whose figure is like this. This is minus 2 to 2, and this the y-axis is 1, and which we can apparently see as it is non-negative. So we know that it can represent an autocorrelation function, And again, we set v equals to omega. We have s omega equals to sine omega square over omega square, which is definitely larger or equal to 0, which means it's not negative. So we know it also can represent a spectral density function. And for sub function c, it is fv equals to 1 when v, absolute value of v is smaller or equal to alpha, and 0 otherwise. And we can see it is very similar with the example we have on the note page 61. So we know actually its figure is like this, and its Fourier transform format will be like sine alpha omega over omega, which figure is like this. So we know that it is not a non-negative function, so we know it cannot represent an autocorrelation function. But after set v equals to omega, we have this s omega, like it's equals to 1 when absolute value of omega is smaller or equal to alpha and 0 otherwise, which is non-negative. So it can represent a spectral density function. And that's all for the for the question 2. So thank you.